Awesome. Well, welcome everybody. My name is Matt Carl. Thank you for coming today to listen to Nigel and myself talk about preventing AWS crypto mining attacks, specifically ones rooted in and around moving in and around the IAM framework of AWS in order to leverage AWS in ways that you do every day, but hopefully somebody else does not do in order to steal power resources from you, basically showing up on your cloud bill. This is timely. Obviously, we did. Actually, let's next slide, Nigel. I should introduce us first. That would be nice. So who am I? I'm Matt Carl. I'm head of product here at Sonrai Security. So my focus is on the problems that our customers face in securing IAM and their entire AWS infrastructure, and what we do here at Sonrai. And with me is Nigel. Nigel, please introduce yourself.
Yeah, so my name is Nigel Sood. I'm a cloud privileged threat researcher here at Sonrai Security. I spend most of my days digging through all the new identity and access management permissions in AWS and other clouds and figuring out how attackers are leveraging the permissions that you use every day in their attacks, like we've seen last December.
There's very few days that go by when I don't get a Slack message from Nigel that says, "Oh my, ... So as he digs through AWS and all the other clouds, interesting things come up, and this was one of them. So Nigel, next slide, we'll just jump into why are we here. So late last year, I think it was actually the GuardDuty team over at AWS disclosed a crypto mining campaign that they had seen take place in some of their customers. And they were kind enough to blog about it and talk about the architecture of the attack, and offer some insight and understanding as to what did the nefarious actors do, how did they accomplish this. And they even went as far as, they've made some updates to their infrastructure on the GuardDuty side to help with detection. And they did propose a bit of action that can be taken on behalf or on your behalf or in your cloud in order to try and tackle some of this to prevent these things from happening. Obviously, GuardDuty looking at what's going on. We always are interested in, can these be prevented? Here at Sonrai, we spend an awful lot of time looking at IAM in all of these clouds and how does privilege work in these clouds and how do we do things in these clouds and how can we protect them at scope and scale? Obviously, least privilege at scale is a difficulty. Anybody on this call who has tried or is actively trying to clean up the IAM overprivileged problem in their cloud, this will be near and dear to you. This particular attack was really interesting to us because it used your cloud or the customer, unfortunately, the victim's cloud in this case, it used it in the same way that they use it. The identities that were involved did things that those identities do. These are permissions that were leveraged, that you have identities that you use day in and day out that make your cloud what the cloud is. This was not some fancy zero-day exploit. This was not some edgy niche case thing. This was simply, I got into your cloud and based on how your privilege was configured, I'm able to do all of these wonderful things, including run your cloud bill up astronomically. Well, I get to leverage it for my crypto mining capabilities. So this was a unique attack, or not unique, unfortunately, not a unique attack, an interesting attack. This is not unique. And when Nigel goes through this today, we're really going to dissect this a little bit and show you guys how this attack unfolded and the permissions that were involved. And we will offer some insight. How could we fix this if we wanted to fix this in our own cloud? And then obviously we do want to talk about how we would fix this and what a cloud would look like if Sonrai was involved. But we'll jump through this pretty quick. I want to get Nigel up to the point where he's giving you a quick demo and dissection, because that's the interesting part of this. I'll stop talking here in a minute. Nigel, next slide.
Sure.
Why do these attacks happen? This is just AWS. Obviously, we're here based on an AWS crypto attack. This could have just as easily have been any of the other major cloud vendors, right? This just happened to be disclosed by the AWS teams. So don't think for a minute that this is an attack on AWS. This is how clouds work. To give you some idea of why these things happen, if we look at any one of the clouds, I'm gonna look at AWS here because that's what we're here talking about. There's 18,911, that's actually low. Another thing that Nigel does for us, him and his team actually look at a constant flow of permissions in AWS and GCP and Azure, all of these clouds. And what do these permissions mean? This number is actually now about 19,500 and something. And that number changes quite dramatically in the span of a month. AWS releases new services and capabilities, including services, 250 plus services, actually closer to 300 services in AWS. And then if we look at what does that mean to you as a cloud operator, you use these services, i.e. these permissions, to basically run your cloud. You're using EC2 to run compute. You're using Identity Center to allow users to SSO into your environment. And this is all done by aggregating permissions up in policies and assigning them to roles or identities in that cloud environment. And how many identities do you have? Again, it's going to depend on the scale of your organization. We use an average of about 11,000. Now that's an average. A lot of small customers that run around with a few accounts. Some customers have upwards of 500,000 identities running around in their cloud because they have hundreds, if not thousands, of AWS accounts. So this number just moves all over the place. But the net result is, and this doesn't matter, if this number is 11,000, if this number is 90,000, if this number is 150,000, 45% of these at least will have permissions that we're going to talk about today and do not use them. Right? They have them. They've gotten them through the, collecting of permission over time. They've gotten them because it was easier to give EC2 star than it was to figure out the 16 permissions that identity needed. None of it is generally malicious. It's just the realities of building a cloud that's a production entity that needs to move forward. We need to add features or release product. And with that comes identities that need to service it, and often a loss or a little bit less focus on what is the true privilege that these identities need in order to get their jobs done. In that confusion of 11,000, 20,000, 50,000 identities, thousands upon thousands of permissions, we find really interesting paths to work with these permissions and do fun things or nefarious things. We can put these permissions together almost like Lego to accomplish a task that you would do every day, like standing up new EC2 or new ECS infrastructure in order for your teams to do their job. We can also stand those same things up using those same identities to do things that you wouldn't have intended us to do. And therein lies the actual, the problem of tackling this type of attack. It looks like you an awful lot of the time. Right? It looks like identities that you have that do their jobs. Yes, they may never have stood up that much. So unless you're running a whole host of products looking at analytics around usage and patterns and nefarious behaviors and things out of the normal, this largely just goes unseen. And so that's why we wanted to talk about this attack and why these types of attacks can happen in these environments. This isn't a traditional vulnerability problem. This is just your cloud. This is just how your cloud runs. Next slide, Nigel. So I want to talk about permissions a little bit. Nigel, I just wanted to throw to you, when we talk about permissions in any of these clouds, what are we actually talking about? What are these things that we call permissions, and what does privilege look like?
Yeah, so permissions are basically entitlements to do specific actions. Basically, everything you're going to do in AWS or any of the other clouds, you're going to be making specific requests to do specific things. You might be listing roles in identity and access management. You might be creating an EC2 fleet. You might be passing a role in IAM. And every single one of those is gated by its own permission. And that's why there's so many, 19,000 something in AWS right now. It's because those basically cover the broad spectrum of everything an identity could possibly want to do in AWS. And every identity, depending on what it's going to be doing, whether it's a human user, whether it's a machine identity for one of your computes, whether it's an execution role for some service, it's going to need some kind of tightly scoped combination of these permissions in order to perform every single thing it needs to do. But it's really hard to come up with that set. And a lot of these permissions are used for very legitimate things. A lot of the EC2 permissions, ECS permissions that we're going to be looking at later on in the demo, they're things that your DevOps people and your infrastructure roles are going to need to be doing in order to keep your production applications up and running. In short, a permission is basically an entitlement to perform a very specific action, and whether that action is benign or nefarious is sometimes hard to tell.
Makes sense. And I mean, I don't know of everybody on this call, but if you look at this list of permissions, obviously, when we talk about privilege, I think you would look at these and say these are privileged. But this attack still happened and is still happening. And things like this happen. So why, next slide, Nigel, why did PAM tools miss it? Why did all of the security tools that we have miss it? Let's not necessarily pick on PAM, but in PAM, privileged access management, why did these tools miss it? And I think in here lies the definition of privilege. Privilege in cloud is a bit of a unique entity in my eyes, Nigel. I mean, when I look at that list of permissions, modify instance attribute, That doesn't scream necessarily as being wildly privileged. I can certainly see that it's modifying something. But why is it not just as simple as all of those identities that have those permissions are obviously privileged and they are protected and no one can ever use them to do things that they shouldn't? Why did the tools miss this, Nigel?
Well, again, it's because a lot of those permissions are scoped to the identities that need to use them. And in an ideal world, there might be an identity that has one or two privileged permissions because it legitimately needs it, but otherwise doesn't do anything privileged. And so the traditional kind of way of categorizing your identities into admin or non-admin or sensitive and non-sensitive, the way you would to gate access to certain identities with a traditional PAM tool, is a little bit more finicky to do. If you could go and tell me in your AWS environment with 5,000 identities exactly which ones have privileged permissions and exactly which ones don't, then yeah, maybe traditional PAM would work, but I think you'd be hard pressed to perform that exercise to begin with. And in this case, it all is identity based. It's not necessarily secrets that need to be protected. And in terms of understanding what privileges contribute towards whether an identity has access to privileged permissions or to privileged API actions, the definition of that privilege is going to change all the time. In a few slides ago, we had listed that there were 18,000 and something permissions that were available in AWS. The number changes literally every day. I have an alert that comes in every morning to tell me what new AWS permissions exist. And so the things that are available, especially if you're giving star or service star permissions to identities in AWS, it's really hard to know what type of privileged access an identity has when it's changing all the time and when it's hard to tell if an individual privilege or permission is privileged or not.
And I think there's me personally, I think another interesting part of this whole thing, and when we look at how attacks like this unfold, and it's not necessarily true of this specific attack, but attacks like this, I need access to those permissions to get this attack done. I don't necessarily need one single identity with all of these permissions. Do I, Nigel?
No. So this attack leverages a bunch of permissions all in a chain. It's doing infrastructure stuff, it's doing discovery stuff, it's doing persistent stuff. A single identity doesn't need to be done or doesn't need to exist with all of those permissions to perform all of those steps. In the cloud, you'll often find a very convoluted mess of trust access between roles and users. If I were able to compromise an IAM user that has access to 3 or 4 different roles, and between those roles, I have all the different permissions that I need, I can still perform this attack just by assuming those different roles for all the different steps. So it is certainly not going to be as easy as, when we go through this demo and then we highlight all the permissions that are used. It's not as easy as looking for identities with that entire set of permissions. You need to look for identities that can eventually reach out and grab those permissions from various locations. Because any combination of compromised identities with these permissions can be leveraged just as easily as one identity with all of these permissions.
Which is interesting because it actually highlights the need to focus on the actual privilege itself, not necessarily on the individuals or identities. It's protecting the permissions, protecting the privilege. Therefore, whoever's calling it will get caught in the mix. I think I followed you there correctly, Nigel.
Yeah, exactly, yeah.
All right, let's jump into it. Let's take everyone through this very quick and give them an idea of how did this actually unfold. And I was actually quite shocked at how quickly this actually happens, right? So within about 10 minutes of getting into the cloud, we've got crypto mining clusters running and doing wonderful things and chewing up cloud bill.
Yeah, so phase one.
Small.
Oh, sure. I'll
and your font, I can't read it. I don't know if everybody else can, but
let's see if I can make this a little bit bigger.
There we go. I can see that.
All right, awesome. So this attack took place over the span of a few different phases. They got initial access. They performed some discovery to figure out what they could do and what resources they could reasonably stand up. And then over both ECS, so the Elastic Container Service, and EC2, the instance service, they stood up a bunch of compute infrastructure containing crypto miners in both of those services. Crypto miners, being malicious computes that will go and do some crypto mining and send the results back out to whoever stood it up. Then they performed some hardening. Phase 1 is initial access, phase 2 is discovery, phase 3 is the infrastructure setup. Phase 4 is hardening and persistence. So they took some steps to make sure that infrastructure stayed in place, and then they created some persistent access to the cloud. And so we'll walk briefly through all of those steps. Initial access is pretty easy. We're not really going to simulate that. Initial access can come from a bunch of places, and it doesn't really matter. In this case, I believe it came from a compromised identity and access management user. Really, it could come from exposed access key credentials. It could come from vulnerabilities, exposing execution role credentials in your web apps. It could come from phishing. It could come from trusted third parties that you give access to your cloud. And it could come from insiders. So in our case, I'm just going to log into AWS and assume that my account has been compromised and then act as an attacker to perform all these steps. And then it's important to note that in the AWS disclosure, they noted that the compromised user had admin-like privileges. Not necessarily an administrator account, but just something that had the requisite permissions. And so my account right now is set up with all the permissions necessary for this attack that the attacker would have performed. So we'll talk about discovery, and we're really focused on setting up that compute infrastructure. So we're going to keep the discovery very limited to, 1, what the attacker did, but 2, focused on EC2 and ECS. And so one of the really easy ways to figure out what we can do in terms of EC2 instance setup without hitting any service quotas and firing off alerts about that is to actually check the service quotas. So there's a whole bunch of service quota codes that AWS enumerates. This one, for example, is for running on-demand standard instances. I am going to be using the AWS CLI for a lot of this. The attacker themselves use Boto 3 in Python, but I don't expect everybody here watching to be super familiar with Python, so we'll keep it simple here. But you can see that with this command, get service quota, we can see that we can have up to 256 on-demand standard instances. This is actually a bit of a misnomer. We can have 256 vCPUs that are allocated towards on-demand standard instances. And one of the important things in here in this response is the usage metric. This is actually the configuration for a CloudWatch query where we can actually go and see, here we've got the quota, but we don't actually know what the utilization is. We don't know how many instances are actually already counting towards that. But using our usage metric, we can go and craft a CloudWatch query that will go and tell us exactly what's being used. So right here, we've actually got nothing in our metric results, which means 0. We've got up to 256 vCPUs for on-demand standard instances, and none of it's being used. You would see values in there if we had anything. If we had 2 instances, you'd see 2. But this tells us that we can spin up to 256 vCPUs worth of standard EC2 on-demand instances and not hit our quotas. So that's how we figure out how many EC2 instances we can set up. You can also do this for plenty of other instance types as well. There's a couple dozen spread out between on-demand and spot instances. I could use a whole bunch of different quota codes to go and check all of those and then stand up as many as I could with all those different instance types. This is just one example. The next thing we want to do is actually figure out if we have permissions to do the thing that we want to do. I could go run some IAM commands and try and figure out what policies are attached, but really that doesn't matter. I just want to know if I can do the thing. And so what the attacker did in this case was they actually ran a run instances command with the dry run flag set. And it doesn't really matter what the instance type or the AMI is. What they wanted to see was whether this command says it would be successful or whether this command will return an error for permissions or for lack of permissions. So you can see right here, request would have succeeded, but dry run flag is set. If I didn't have the right permissions to run instances, I would be seeing a different permissions error. And that's really all that we know that the attacker did in terms of discovery. We know that they checked quotas, and we know that they confirmed their permissions using dry runs. And then from there, we can jump right into setting up our infrastructure. So I'll do the EC2 side of things, the ECS side of things. The EC2 side is very, very similar. So we'll just go through one of them. So for the Elastic Container Service, actually setting up our crypto mining infrastructure, we need to understand how ECS works. So ECS, we have kind of a hierarchy of resources. We've got at the top, we've got our clusters, and those clusters will contain services. And within those services, there will be tasks, and within those tasks are are containers. And it's the containers themselves that are going to be containing our crypto mining infrastructure. So we kind of need to set this all up sequentially, but we can start with our container. So we're going to create a cluster that will run Fargate-based tasks and containers. And then from there, we need to create a definition for our tasks.
And so, Nigel, in 2 commands, I've already set the foundation for the infrastructure.
And that's exactly it. Yeah. So we've created a definition for our task, and here is where you are referencing all the malicious infrastructure. So I've made some changes between what the attacker actually did and what we're going to do, because I don't want to actually stand up malicious infrastructure in our development environment or in our sandbox environment. So this task definition right here is just saying we're going to stand something up using Fargate. We're going to use an AWS VPC for it. I want a certain amount of CPU and memory allocated towards it. The attacker actually used much higher values. But the main thing here is that for the tasks, the attacker put maliciously crafted container definitions in here. So this Alpine latest is a reference to Alpine Linux. This is the Docker Hub image for Alpine Linux. The attacker was using a maliciously crafted Docker Hub image that already contained all the crypto mining infrastructure on it. And then their startup command kickstarted a shell script that existed on that malicious container image. Here, we're just using Alpine and we're using some benign command. But if you point this at a malicious image and then you run some startup script using the command, that's how you would kickstart the crypto miner. So this hasn't stood up any infrastructure yet. This is just a task definition that we're going to use to go and spin up a bunch of things within our cluster that we just created. So the next step, we're actually going to need the revision number of the task definition that we just created. So I'll go ahead and store that in an environment variable. And we're going to need somewhere to put our container instances. If I were actually performing something malicious here, I would want to be putting them in a VPC where those task instances and those containers would actually be able to go and phone home as they're performing their crypto miner tasks. But here we're just going to put it in the default VPC. So I've got the default VPC, the subnets, and the security group. Just something that I'll need for the next command, which is creating a service for our cluster. So we'll create a service for the cluster that we just created. We're going to use the task definition that we just created that has our malicious container configuration in it. And we'll say that we want 2 tasks per service. So when I run this, it'll start the service on the cluster, which will hopefully spin up 2 instances of our quote unquote malicious task. And then we'll actually go into ECS and see if this worked. One more thing to note, we're using the same networking configurations that I just pulled into environment variables, and we're using Fargate as our capacity provider. The attacker themselves actually went a little bit more complex with this. They played with a more resilient capacity provider strategy, where they were using Fargate and Fargate Spot. But for the purpose of illustration, this should work. And if I go and pull up my AWS account and go to ECS, we should see everything stood up there. So you can see our crypto cluster with 1 service on it. We can go in here and take a look at the tasks. And you can see that we've got 1 task that is currently provisioning. And if we go in here, you can see that it's the Alpine latest URI, and you can see the command. If we go all the way down, you can see that it's still in the process of standing it up. And you can see that we don't have any logging options configured. As an attacker, you wouldn't want to leave more of a footprint than necessary, so we didn't add any log driver logging to this ECS container. So you're not going to see as much in CloudWatch as you normally would want to see for an ECS container. But we've got it running. And if we gave this a little bit more time, it would spin up the second one as well. But we'll keep moving a little bit. This was mainly just to show that with those 3 commands, we were able to set up something that would go and spin up several instances of some task. And the numbers that we were using were pretty light compared to what the actual attacker was using. In the attacker case, they were using upwards of 50 clusters per compromised AWS environment, and then on those clusters, they'd be running services with up to 10 tasks per service rather than just the 2. So it really quickly goes from the 2 that we configured it to set up to hundreds or even thousands of malicious containers running, using and chewing through a whole bunch of compute.
So what, Nigel, I think what you've shown so far is we've managed to get the infrastructure stood up. It's about 3 commands. We're running, we're now crypto mining. The permissions that were used are not shocking to anybody. They're ECS creation capabilities, EC2 permissions, in order to create these task definitions, things like that. Again, these exist in everyone's cloud that uses these services. Many identities have these. I challenge anybody on the call to be able to go through your cloud and figure out every one of the identities that has these permissions and every one of the identities that requires these permissions. These aren't shocking. These aren't being misused. These are Nigel's using these exactly as your ops team uses them in order to stand up their infrastructure, as your terraformers use them. The interesting part here is what identities have them, what identities use them. Can you attest to those, and are they the ones that should? Right. Now let's talk about persistence, Nigel.
Yeah. So I will note before we get too far, there was the whole EC2 side of things as well, where they were using launch templates to go and stand up EC2 infrastructure and then creating auto-scaling groups to spin up a whole bunch of them at once in a resilient way. And they actually did something really interesting on the EC2 side, where they would use modify instance attribute to disable API termination on those instances to make it really hard to shut them off. But a lot of that is basically exactly the same as what we saw with ECS, where you create a template and then you go and scale up using that template. So yeah, we'll talk about persistence. And there were 2 ways that the attacker persisted access in AWS in this specific attack. We'll talk about the easy one first and then kind of go to the hard one. So the easy one is doing the classic identity and access management based stuff. They created a new identity and access management user. They assigned some permissions to it. In this case, they were using SES, simple email service access, to grant this user permissions, evidently for some sort of phishing-related activity in the future. And then they gained persistent access to this user by creating an access key on it. And so here, normally, there would also be a secret included in this output. I have it filtered out right now. But with the access key ID and the secret, they would have persistent programmatic access to this user, and therefore the permissions included in this IAM policy. They also, for good measure, created a login profile on that IAM user. So they created a password for it so that they could go and actually sign into the AWS console if they need to. So 2 ways of access to the user, via console login or via access key, and then the permissions assigned to that user would actually grant them privilege when they log in. This is like bread and butter classic.
I was going to say, this is 101 for getting persistence, right? And
yeah,
we all know that this exists, and therefore we all know every single identity that can create a role, every single identity that's allowed to cut an access key, every single identity that's allowed to assign passwords to identity. These are all super controlled. I say that with a smile. I wish it was. It's not uncommon to see hundreds of identities and accounts that can do anything I just said. It's just the reality of how these clouds unfold when we actually roll them in. But that's persistence 101. What did they do that was advanced, Nigel? What was that? I like the other one way better, because this is one.
Yeah, so the more advanced thing that they did was actually using Lambda functions to perform something similar. They used a publicly accessible Lambda function with an execution role that they themselves configured. And we're not 100% sure exactly what was in the code of this Lambda function based on the AWS disclosure. It seems that they were using it and the code itself to leverage the execution role credentials to keep those ECS services up and running. They created a publicly invocable Lambda function that when they went and pinged it, would go and make sure that the amount of ECS services that they wanted were up and running, or it would go and spin up more. But it's not 100% clear that that's exactly what it was doing. And so I really wanted to leverage the exact permissions that they were using to kind of show what the worst case scenario would be for a publicly accessible Lambda function with execution roles. And this is a way of persisting access more than anything. We'll consider a case where the bad actor leverages the function to basically retain persistent access of the IAM credentials themselves without needing to create an access key or an IAM user or anything like that. And so we'll start with creating the execution role for the Lambda function. So we'll create a role called Lambda executor, make sure that it's assumable by the Lambda service, and we'll go ahead and attach the Lambda basic execution role permissions to that role. I am storing the role ARN in an environment variable because we'll need it in a little bit, but we have this role that has the Lambda basic execution role permissions and is assumable by the Lambda service. Then we need to create our Lambda function. And this Lambda function is going to be dead simple. This is our Lambda function, specifically this right here. Our function handler, so when we invoke the function, it is going to return credentials, and the credentials are just the Bodo3 credentials configured to the Lambda function. It is that simple. It's 5 lines of Python code. And all it does is it returns the access key ID, the secret, and then the token associated with the execution role of the Lambda function. For 5 lines, this is a pretty nefarious function. So we've got that zipped up. We'll go and create the Lambda function. So using the execution role ARN that we just created, using the zip file that we just created, and then pointing ourselves at the right function. And so we've got our function created. This isn't publicly accessible yet, but because I created it and because I have the requisite AWS permissions with what I'm configured as right now, I can actually go and invoke that and see if it works. So I'm going to go invoke the Lambda function and store the output in this creds.json file. So we can see that it was successful. And then if I go and load the credentials out of that JSON file and then run a getCaller identity command, I should see that I'm actually able to run AWS CLI commands in a subshell using the execution role. So you can see we loaded the credentials out of the file that was returned by the Lambda function. And then when we ran getCaller identity after configuring those credentials, you can see that that command was run as the Lambda executor. So anybody with permission to go and invoke this function can receive on-the-fly credentials that they can then use to go and do anything that that Lambda role could do. Now, this isn't publicly accessible yet, but we're getting there. And that's exactly what our next 2 commands are going to be for. So first, we need to create a function URL configuration. This basically creates a publicly accessible URL that when invoked, or when that URL is hit, it'll invoke the function. And right here, we're going to configure it with a none auth type, and we're going to store the URL in url.txt. And basically what the none auth type means is that I don't need to be signed into AWS. I don't need SigV4 signing or anything like that in order to be able to access this URL. And the last thing we need to do is add a permission on that Lambda function that says unauthenticated users are able to invoke the function URL associated with the function that we created. And that should be done. Right now, we should have, with 4 or 5 commands, a Lambda function with role credentials associated with it, where somebody from completely outside can go and ping a publicly accessible URL and get that role's credentials, and then go and do anything they want in the cloud using that role's credentials. And when I had assigned the basic Lambda executor permissions to it, I could have also assigned administrator access permissions to it. And then anybody from the outside who has that URL can at any time go and perform star permissions inside your cloud. So to show that this works, we'll go and open a new window. And just to show that I don't have any AWS permissions configured right now, I've got nothing. Nothing's configured. I'll go and curl the URL that we had just created. So I had it stored in url.txt. We'll go and curl that and store it in creds2.json. And then if I go and do the same thing that I had done before, where I go and load those credentials and then run a getCaller identity command, you'll see again, we've got that Lambda executor role. So we've set up a Lambda function that you can go and hit from anywhere in the world, and it gives you role session credentials. And they are short term, but then you can go ahead and and ping that function anytime you want to get new credentials. No access keys required, no login profiles required. The only thing that I needed to do in the identity and access management service at all was create the execution role for that Lambda function. And if you already had privileged Lambda execution roles, I could have just reused one of those. I didn't necessarily need to create a new one. So this is a way of creating persistence with Lambda without necessarily needing to touch all of the standard persistence API actions in the identity and access management service.
That's
And
crazy.
that's really it. We did our discovery. We figured out what we could set up. We performed the actual infrastructure setup. We demoed the ECS side of things. There was also the EC2 side of things. And then we performed our 2 persistent steps, the Lambda-based one and the IAM-based one.
We did it all in 20 minutes.
Yeah.
So that's how easy. Now, I did want to, if you jump to the next slide, Nigel, I did want to talk a little bit very quickly about this. So Nigel, when he looked at this, I think you had 2 slides of permissions here. We have ECS permissions, EC2 permissions, IAM permissions, Lambda permissions. The goal here was not to look at these permissions and say, oh my goodness, these are obviously privileged. Well, no, yes, they are. I don't think anybody on this call would look at create role and say it's not privileged, or look create user and say it's not privileged. The goal here is, and the point is, these permissions are used all the time in your cloud. Many identities have them. More identities have these than you know have these. This is not a scenario of AWS had a problem. This is a scenario of every cloud has a problem, and it's an overprivileged problem. What was quite insightful and interesting was the disclosure that AWS made. I think, Nigel, if you hit next on this, you're going to talk very briefly. This is what AWS told us to do to fix it.
Yeah, so AWS gave exactly one kind of remediation that would actually do something preventative. They also added a bunch of guard duty findings, which is super helpful. But from a preventative remediation side, they gave us one SCP, and it was to deny create function URL config and update function URL config. And this was the step when we were doing our Lambda persistence, where we went and created a URL that could be invocable from anywhere in the world to go and invoke that Lambda function. But this is really only tangential to the actual infrastructure setup that was setting up the crypto miners. This was just kind of an auxiliary part of the attack that, yes, 100%, it's great to be able to block this, but this doesn't prevent the attack in the first place. So the question becomes, why did AWS do this? Why is this the only thing that they gave us in terms of preventative action? And the reason is because it's really the only thing that they could do. From an SCP standpoint, service control policies, implementing centralized identity and access management controls, it's really the only thing that they could suggest, because looking back at the other permissions that are used, everything in here is used day to day within your cloud by legitimate identities with legitimate reason. That, we get to that operationally risky bit. If you block any of those other permissions that were used as part of this attack, you're going to cripple your cloud.
That's the interesting part about this to me. Every one of those, again, those of you on this call with 100 accounts, your problem is big. Those of you with 50 accounts, your problem is still big. Those of you with 800 accounts, 1,000 accounts, your problem is immense when it comes to how many identities have these permissions that we're talking about and can leverage them versus the ones that should have them and do use them every day. And AWS has said, you could go fix the Lambda thing, stop the Lambda thing from happening. Right? But didn't really address the fact that with normal permissions that are granted to hundreds, if not thousands of identities, these actions are doable every day within these cloud environments. And we can't stop them, because if we did, we'd break your entire cloud with an SCP that we stuck in at the top that said, don't let anything called create role. Right? It's just not possible. Let's move on, Nigel. Let's quickly get through this. Why are we here? Obviously, we're Sonrai. We think this problem is not unique. We think this problem is basically endemic of how clouds operate. You have huge numbers of identities, huge amounts of privilege associated with those identities. Privilege looks different in cloud. We're not used to looking at privilege being 2,000 distinctly defined API calls that we have to worry about. That's what we do. So what we do with the Cloud Permissions Firewall is understand every single identity in this world, every single thing that they do. And when it comes to least privilege, at a click of a button, we can start to claw back all of that privileged access that they do not require, so that when somebody gets into your cloud and they get their hands on an identity that has admin-like privileges or any 2 of the permissions that we talked about, and they don't use them, it's not part of their normal day, we'll have taken those away and protected that identity from those in a way that scales immensely across the cloud. Click of a button, hours of time, not months or years of time, trying to address every single policy on every single identity, which is the true least privilege way of, quote unquote, solving this problem that's not really attainable in any scaled cloud that we've ever encountered. So the Cloud Permission Firewall delivers this at a click of a button across all of your identities, ensuring that you don't break your cloud, but you do achieve the protection that we're talking about, which is, yes, we can absolutely control create role, and we know exactly who should have it. And when it's used by somebody else that is not supposed to be doing it just because they have it, we'll get in the way. We'll start letting people know. Nigel, I'm going to give you 1 minute. Can you show me what this looks like?
Absolutely. So I'm going to go sign into a different AWS environment where I have Cloud Permissions Firewall protections in place. And I'm just going to real quickly copy paste a few of the commands that I was using before. We'll try registering an ECS task definition. And you can see that I was denied with an explicit deny. I'll try, I'll do one of the EC2 ones that we didn't show off before, but I'll try creating an EC2 launch template with some malicious startup script embedded in it. I get denied again, and then I'll try one of those persistent steps. I'll try creating an IAM user. And you can see that I'm still not authorized to perform that. So that same those same three commands, I was getting denied. And if we actually go and take a look at the Cloud Permissions Firewall, we'll see not just that this was able to be stopped.
My phone was buzzing like mad, so I'm assuming that I've got a bunch of access happening.
And so you can see the first thing we see in here in our approval stage, you can see that I recently requested to access to the EC2 create launch template permission in the account My Health Production, and I can either approve or deny that. In this case, where I'm an approver, ideally you would want somebody else approving my requests. And then you can see that there was also a request that came in for IAM create user. If we gave it a little bit longer, we'll probably see the ECS one as well. But this was basically just to show that we can set up a system whereby if I want to use something privileged, there's a human in the loop. I get denied the first time I try to do it, but the notification goes through to say, hey, this person's trying to do this thing. Do you want to approve or deny it based on whether there's a legitimate use case or not?
Absolutely. Thank you, Nigel. And
that's the 1 minute.
That's the 1 minute. And I mean, therein lies the rub. Every single human, every single role, every single execution, every single Lambda execution role falls under the purview of the firewall to protect, understanding what that identity normally does, what it should be doing, and when it does something weird or unexpected, that's when we step in the way and we start alerting people. The interesting part about the firewall in this particular attack is the minute they started setting up infrastructure, everyone in the organization would have known it was happening. And they would have been stopped at that point. This wasn't about a guard duty finding saying this is happening in your world. This is all about somebody tried to do something. They've never done it before. We've stopped them. Should this be happening? Yes or no? Next slide, Nigel. I think we had 1 minute and 30 seconds for Q&A. I don't know if anybody has any questions. I do apologize. We're running a little up against time, but if there's any questions, we certainly will take them now. One thing I did want to talk about while you guys type is we do offer 14-day free trials of the Cloud Permissions Firewall. Fully functional, not hindered at all. Simply go to the Sonrai website. You can sign up, onboard your cloud, and you can see everything that Nigel just showed you. You could actually simulate that same attack and see what would happen in your world if you put controls in, or if you have identities that would have been exposed to this type of scenario. So certainly, please, anybody who's interested in what we do here at Sonrai, we'd love to work with you. We'd love to show you what your cloud looks like and what could occur in that environment, and how easy it is, or how easy it can be, to actually roll up protections and actually apply them to your world. And I don't see any questions coming in. We'll probably rate up. Oh, wait. We don't have this third-party tooling. Can you recommend anything else we can do? I think I'll hand that one to Nigel. Nigel, what was your comment? I asked this question to you. If I don't have CPF, what do I do?
Yeah, well, so I think AWS really hit the nail on the head. They gave an SCP that is a good SCP. 100% you should use it. If you don't need publicly accessible Lambda functions, deny create function URL config, update function URL config. But for all the other permissions, you really need a deep understanding of which identities need access to them and which ones don't. You can use AWS Access Analyzer to help with that. But if you've got hundreds of accounts, even tens of accounts with lots of identities in them, that's going to be a really hard task. But least privilege really is the answer. Make sure that only the identities that need those permissions have those permissions, because otherwise you end up with what AWS described as admin-like IAM users that can perform attacks like this.
And we'll leave you guys with that today. The answer is go do least privilege in your cloud for every single identity that you have, or come talk to us. We'd love to show you that there's a better and easier way to do this that scales with you as your business moves forward and takes these sleepless nights out of your way. So thank you everyone for coming today. Apologize for running slightly over. Look forward to talking to you guys the next time around. Enjoy the rest of your day.